Hey, what's up, you guys? This is Lab 2, Charge Tapes 2, the second one, Lines of Charge. So here's our introduction. So some of our main physics principles here in Lab 2 are Coulomb's law, which states that the electrical force between two charged objects is directly proportional to the product of the quantity of charge on the objects and inversely proportional to the square of the separation distance between the two objects. And here's the formula for Coulomb's law underneath our definition here, and that's 1 over 4 pi epsilon naught times q1, q2 over the vector r times r hat, the magnitude of the vector r times r hat. So 1 over 4 pi epsilon naught is also equal to 9 times 10 to the ninth, and then q1 and q2 are just our charges. Other important parts of this lab are electric fields, electric forces, line charges, and everyone's favorite Physics 1 classics, Newton's third law, which states that all of the forces between two objects exist in equal magnitude and opposite directions. So, equal and opposite, that's our big thing with Newton's third. So in lab 1, we had our two charge tapes, and we were just trying to, they were point charges, and we were trying to determine the, charge and the magnitude of the gravitational force. Here, instead of looking at the tapes as point charges, we're looking at them as line charges. So when you think about charges, just imagine one long line, and all of the tapes are just it's a line made of just infinitely small pieces of tape, and each of these small pieces of tape have their own point charges. So it's just kind of like a line of connected point charges. Also, we have this really sick frog that you can get tape from, and I swear this is not a Scotch tape ad, but he's pretty great. So here's some of my data and measurements. So my tape length was 0.25 meters. My tape mass for one piece was 0.0025 kilograms. The distance between the two tapes was 0.03 meters. And the magnitude of the gravitational force is given here in newtons, and you have the electric force in newtons per coulomb, and then the magnitude of the overall charge in coulombs. And I don't really want to say those numbers, so you can read. Also, here's this monkey, and I think he's pretty cool. Again, this is not, Scotch tape is not a sponsor. So some of the main questions in this lab were, what if you had modeled each of your tapes as a single point charge like in the previous lab? Compare the estimated value of the charge you get when you use your experimental data to produce a point charge model to the value you got with your line charge model. So the charge value, if we were still using just a point charge model here, our values would look the exact same as they did in lab 1, because that's literally lab 1. But when you do the line charge model, you get a slightly larger and more accurate value for charge, because you just have more charges available, and you can always get a better estimate whenever you have more points to look at. And so the second question is, why do these estimates differ? Which value is more likely to be closer to the real value, and why? So the estimates differ because the manner of overall calculation is different. So the point charge model really just looks at y values, but the line charge model takes the x values into account, and that's more of a real world kind of scenario, because our world is not just y values, we're not just all going up, 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 that's just not realistic. And so overall, your line charge value is going to be closer to your real value because of the inclusion of x and the overall inclusion of more points on that line than just a single point. So here's my code. That's pretty much my code. We all had the same starter code, so I feel like I don't really need to explain it, but that's it. That's how you find all of the things. Anyways, make sure to subscribe to my channel. I put out new videos every other week. Bye!